So in today's lecture, we are going to learn about the encoders. Now an encoder is a device actually whose inputs are decimal digits and or alphabetical characters and whose outputs are the coded representation of those inputs. That is, an encoder is a device which converts familiar numbers or symbols into a coded format. In other words, an encoder may be said to be a combinational logic circuit that performs the reverse operation of the decoder. Thereby, the opposite of decoding process is also called encoding. Okay. So an encoder is an electronic device used to convert an analog signal to a digital signal such as a BCD code. It has a number of input lines, but only one of the inputs is activated at a given time and produces an n-bit output code that depends on the activated input. The encoders and decoders are used in many electronic projects to compress the multiple number of inputs into smaller number of outputs. Very significant. Binary encoders converts in its 2 to the power of n inputs to an n-bit output. Only one high value is presented as input. The result is a binary encoded output of size n. Binary encoders are useful for compressing data. For example, 4:2 encoder. If we give 4 inputs, it produces only 2 outputs. So this is a schematic of an encoder where we have 2 to the power of n input, starting from I0 to the last variable, the last input, and also the n outputs. Now let 4:2 encoder has 4 inputs, Y3, Y2, Y1 and Y0, and 2 outputs, A1 and A0. Okay. So the block diagram of 4:2 encoder will be like this. So this is a block diagram of 4:2 encoder where there are 4 inputs, Y3, Y2, Y1, Y0 and 2 output, A1 and A0. At any time, only one of these 4 inputs can be 1 in order to get the respective binary code at the output. The truth table of 4:2 encoder is shown below. As you can see the truth table. So there are 4 inputs and 2 outputs. Okay. So as you can see here, accordingly the outputs are taken. Okay. So if Y0 is 1, that means A1 is 0 will be 0 0. For Y1 to be selected, it shows 0 1. For Y2 selected, it shows 1 0. And if Y3 is selected, it is binary 1 1. So from truth table, we can write the Boolean function for each output as you can see here. So A1 is equal to, you can see here, A1 is equal to Y3 plus Y2. Okay. So A1 is equal to Y3 plus Y2. And A0 is equal to Y3 plus Y, and it is very evident. So A1 is, you can see here, it's high, A1 is high for these two. Okay. A0 is high for, you can see here, Y3 plus Y1. Okay. It is high for. We can implement the above 2 Boolean functions by using 2 input OR gates. The circuit diagram of 4:2 encoder is shown in the following figure. As you can see here. So clearly A1 is the OR of Y3 plus Y2 and A0 is Y3 plus Y1. Okay. So in this way we can obtain the circuit of 4:2 encoder. The above circuit diagram contains two OR gates. These OR gates encode the 4 inputs with 2 bits. So the second case is octal to binary encoder. What is there? Octal to binary encoder has 8 inputs, Y7 to Y1, and 3 outputs, A2, A1, and A0. So octal to binary encoder is nothing but 8 to 3 encoder. The block diagram of octal to binary encoder is shown in the following figure. So this is the block diagram of octal to binary. Clearly Y0 to Y7 has basically 8 inputs and 3 outputs for octal to binary conversion. Okay, encoding, sorry. So at any time only one of these 8 inputs can be 1 in order to get the respective binary code. So the truth table of octal to binary encoder is shown below. So this is the truth table. It is the same like 4 to 2, but here it is 8 to 3. So the inputs are Y0 to Y7, and these are the 3 outputs. Okay. So as you can see here, if Y0 is 1, so there is 0. When Y1 is 1, it is 1, 0, 0, 1. When Y2 is 1, it is actually 2, so 0, 1, 0. 3 is selected, so 0, 1, 1. 4 is selected, means 1, 0, 0. Y5 is selected, means 1, 0, 1. And Y6 is selected, is basically 1, 1, 0. And similarly for 7, it is 1, 1, 1. So from truth table, we can write the Boolean function for each output as A2 is equal to, you can see here, A2 is equal to, this is A2, okay, A2 is equal to a Y7, okay, A2 is equal to Y7 plus Y6 plus Y5 plus Y4, isn't it? And A1 is equal to, so A1 is equal to Y7 plus Y6 plus, you can see here, Y3 plus Y2, okay, and A0 is equal to, so you can see here, A0 is equal to Y7 plus Y5 plus Y3 plus Y1. So this is the Boolean function realization. We can implement the above Boolean function by using 4 input OR gate. Circuit diagram of octal to binary encoder is shown in the following figure. So this is a circuit diagram. Clearly 4 input OR gate is used, where we put all the inputs and corresponding code is obtained at the output as A0, A1, A2. The above circuit diagram contains 4 input OR gates. These OR gates encode the 8 inputs with 3 bits. Now the drawbacks of encoding or the encoder. Following are the drawbacks of normal encoder. There is an ambiguity when all outputs of encoder are equal to 0, because it could be the code corresponding to the inputs when only least significant input is 1, or when all inputs are 0. If more than one input is active high, then the encoder produces an output which may not be the correct code. Okay. For example, if both Y3 and Y6 are 1, then the encoder produces 1, 1, 1 at the output. This is neither equivalent code corresponding to Y3 when it is 1, nor the equivalent code corresponding to Y6 when it is 1. So to overcome these difficulties, we should assign priorities to each input of the encoder. Then the output of encoder will be a binary code corresponding to the active high inputs, which has higher priority. And therefore this encoder is also known as priority encoder. So let us go in details of the priority encoder. So a 4 to 2 priority encoder has 4 inputs, Y3, Y2, Y1 and Y0, and 2 outputs, A1 and A0. Here the input Y3 has the highest priority. Okay, it's the system priority we designed, whereas the input Y0 has a lowest priority. Okay, so in this priority system, we are given the highest priority to the Y3 input and the lowest priority to the Y0 input. Okay. In this case, even if more than one input is 1 at the same time, the output will be binary code corresponding to the input, which is having higher priority. So basically, we designed a priority based system, where we have given priority to the inputs. Okay, priority to the inputs, so that when two or more keys, like let us say example of a keyboard, when two or more keys are pressed at one time, then priority system has to come into play, so that the input based on the priority system is fetched by the device, and proper output is obtained at the output. Okay, so that is what is actually priority encoding. Okay, so we consider one or more input V in order to know whether the code available at output is valid or not. Okay, so it is signaling bit. If at least one input of the encoder is 1, then the code available at the output is a valid one. In this case, the output V will be equal to 1. So it will signal that. If all the inputs of encoder are 0, then the code available at outputs is not a valid one. In this case, the output V will be equal to 0. The truth table of 422 in priority encoder is shown in the next page. So it comes here, is shown below. As you can see here, this is the truth table. So Y3, Y2, Y1, Y0, 4 inputs. Okay, and 4:2, that means there are 2 outputs, A1 and A0, and this is the signal bit V. Okay, so as you can see here, when all are 0, this is 0. Okay, when this is 1, Y0, so 0 is fetched. Okay, when this is 1, so irrespective of this one, it will be 1. When this is 1, irrespective of whatever is here, it will be selecting 1 0, that is 2 Y2. And when this is 1, so irrespective of whatever is there, don't care conditions, it will be selecting 3 for Y3. Okay, and all the cases signal bit will be high. Okay, so now you see, let us find the K-map for A1. Okay, so this is the K-map. Okay, so for obtaining this K-map, what we should do is, actually you can see here there are 4 inputs. So basically there will be 16 combinations as such, binary combinations. Okay, so you can see here how we will get the combinations. You just put one more K-map over here and put one more truth table over here. So 0 0 0 0, it will be 0 0. So 0 0 0 1 0 0, 0 0 1 0 will be 0 1, and 0 0 1 1, because don't care can be either 0 or 1. So in this way we get all the 16 combinations, and we will put it over here. Okay, so this is the pair over here. Okay, and this is also a pair over here. It will pair all the things. Okay, and clearly we will get Y2 Y3 over here, that is Y2 plus Y3. This is K-map for A0. Okay, here we will get Y2 Y1 plus Y3. The simplified Boolean functions are A1 is equal to Y3 plus Y2, A0 is equal to Y3 plus Y2 bar Y1. Similarly, we get the Boolean function of output V as V is equal to Y3 plus Y2 plus Y1 plus Y0. So in this way, the whole priority encoder system is designed. It's very important from the exam point of view also. So we can implement the above Boolean function using logic gates. The circuit diagram of 4 to 2 priority encoder is shown in the following figure. As you can see here. Okay, it is based on the previous expression what we got. Okay, so A1 is equal to Y3 plus Y2 and so on. Okay, so above circuit diagram contains 2 input OR gates, one 4 input OR gate, one 2 input AND gate, and an inverter. Here AND gate and inverter combination are used for producing a valid code at the outputs, even when multiple inputs are equal to 1 at the same time. Hence, this circuit encodes the 4 inputs with 2 bits based on the priority assigned to each input. Thank you.